Today, we study line integrals. Firstly, we need to develop some geometric notations. Path, a continuous map following an interval AB to Euclidean space is a parametric path. Okay, so a parametric patch is a map. Okay, but this map has an image. The image that is gamma AB. Of course, if you like, you can denote this by this method, but this make the notation complicated. So we might also omit this and simply write the image in this way. And this image is a path. The image is called a path. So parametrized patch and the patch are different. Parametrized patch is a map, but patch as the image of the map is a subset of Rn. So it is a geometric object in our space. Okay, so these different objects, and also the patch has endpoints. That is gamma A and gamma B. Okay, so this is the first notation, very easy. Okay, the second notation is smooth parametrized patch. Smooth. If this map is differentiable for every t in the open interval, exists for t in the open interval. So we can take derivative. Geometrically, derivatives of a vector valued single variable function is the tangent. Okay, we encounter this in the geometric application of partial derivatives. So if this derivative exists and bounded, also non-zero, everywhere non-zero for some b, a positive number. That is for every point in the open interval, the derivative exists, and all the derivatives. That is, we have a derivative function, which is also a map to Rn, but this derivative function gamma prime only defined on the open interval. We do not require it to be defined on the endpoints of the path. For t equal to a or t equal to b, we have no requirement. So this means that this function defined everywhere in the open interval and bounded. That is what we say that the norm of the derivative less than or equal to b. And also we have a requirement that this derivative is everywhere non-zero. This will play an important role in our later discussion, as you will see. Okay, so this is the smooth patch, a smooth parametrized patch. Of course, if the parametrized patch is smooth, then its image is a smooth map patch. Okay, so in this part we have smooth parametrized patch and a smooth patch. It is simply a parametric patch or patch which an additional assumption that the derivative exists and bounded on the open interval. Okay. another case that is piecewise smooth. So if there is a partition of the interval AB, P, a partition of the interval AB is precisely a finite subset of the interval containing the endpoints. So usually we denote it by T0, Ti, I from 0 to M, a partition of AB such that gamma restrict to the subinterval. Then restricting to the subinterval, it is a map from Ti minus 1 Ti to Rn. Therefore, the restriction of the gamma to the subinterval is itself a parametrized patch. Okay, so if we can subdivide the interval AB into finitely many subintervals, so that restricting gamma to the subintervals to every subintervals, the resulting parametrized patch is smooth. Okay, then we say that our parametrized patch gamma is patchwise smooth, and its image is a patchwise smooth patch. So this involving piecewise smooth parametrized patch and piecewise smooth patch. Okay. Now we also have another concept. In the case that gamma A equal gamma B, this means the patch starting from gamma A and then go away and eventually it come back to the same point when T equal to B. Okay. In this case, we said that this patch is closed. This is open. Okay. There's some gap between the endpoint and the starting point. But if the endpoints, if the starting point and the endpoints coincide, this is closed. Okay. So this is the basic notation. And also, geometrically, patch is a subset of Rn of our space. It's our geometric object. But the parametrized patch is simply a map of the geometric object. Okay, we can consider the parametrized patch to be the parametrization or the analytic expression of the geometric object, the patch. But as we know from analytic geometry, a curve or a patch in the space could have more than one parametrization. Okay, so our next concept is related to this property. So suppose we have two parametric patch. Parametric patch gamma AB. This is a parametric patch, and eta is also a parametric patch defined in a possibly different interval alpha beta. We have two parametric patch. We say that they are equivalent. Equivalent means that they express the same geometric object. Okay, so but how to define this concept? If there is a strictly increasing function or homeomorphism from denoted by sigma from alpha beta to AB. Homomorphism means that this map sigma from alpha beta to AB intervals is continuous and it is 1 to 1 and 1 2. Or in other words, this sigma is a bijective bijection. Sigma is bijective, so it has an inverse. So not only sigma itself is continuous, its inverse is also continuous. In this case, we say that this sigma is a homomorphism. Okay. So for these two pairs, parametric pairs, gamma and eta 2 equivalent, it means that there is a strictly increasing homomorphism sigma between alpha beta and AB intervals, such that eta is the composition of gamma and sigma. So what this means, it is better to understand this by a picture. So this is AB. Our gamma is a map to Rn. We have another eta defined in alpha beta. Okay, this gamma and eta are two parametric pairs in Rn, and we say that they are equivalent if we have a sigma from AB interval to from alpha beta interval to AB interval. So that sigma is a bijective, so that it has an inverse. It has inverse. Okay, and both sigma and its inverse are continuous. So if such a sigma exists, so that eta is the composition of gamma and sigma, then we say that gamma and eta are equivalent. It is easy to see that the corresponding pairs are the same. If gamma and eta are equivalent, then it is not difficult to show that gamma AB equal eta alpha beta. That is the corresponding pairs. The pairs corresponding to gamma are the pairs precisely the pairs corresponding to eta. So this is precisely that both gamma and eta are the parametrization of the same curve or same path in Rn. We have a curve in Rn, say, and this curve we have different parametrization. One is gamma, the other is eta. Okay. So this is the concept of equivalent. The key point of this concept is that they represent the same curve, the same path in the space. They represent the same geometric object. Okay. For example, we will give you an example. Gamma t is cosine t, sine t, t 0 to pi, and eta t is t square root of 1 minus t square. So these two maps are smooth parametric patch, but as you can check, their image are the same upper half circles in the xy plane. Okay, so for the gamma, the t is here. For our eta, the t is here. For the gamma, the geometric meaning of the parameter t is the angle between the radius determined by gamma t, which the x-axis. Well, for eta, the parameter t means the first coordinate of the point in in the curve in the patch C. Okay, so C is gamma 0 pi is also eta minus 1 1. Okay, so gamma and eta are equivalent. You can define the sigma, where sigma is given by sigma should be defined from minus 1 1 to 0 pi. So let sigma t to be what? To be cosine t? I think so. Okay, sigma t to be cosine. No, cosine. Then eta t is cosine sigma t sine sigma t. That is precisely gamma sigma t. Therefore, gamma composition with sigma t. Okay, so this shows us that equivalent curve represent the same path in the space.